Good morning, good evening, and good afternoon, wherever you are. And thank you for joining this webinar. This webinar is about using iMachining for tough-to-cut materials. So there are several such materials, and we're going to see some practical tips about how to use iMachining, how to use HSM, mainly for material removal, or volume removal. So let's get along. So hard materials or difficult to cut materials, several of them are there. So we're going to talk about a few of them today. We're going to talk about titanium. We're going to talk about Inconel, stainless steel. These are the three materials, along with the mold steel, which generally mold and die makers cut. We'll not talk about stellite, hastelloy, or even tungsten. We'll talk about. We have a case for tungsten also. So we've cut tungsten carbide using iMachining. So we are going to talk about tungsten also. So basically, this webinar in the next 45 odd minutes, we're going to delve more deeper into the technology of iMachining, how to practically apply iMachining to such materials, what things or how should you look out for tools, how should you look out for lubrication, what should be your work holding, what should be your tool holding, several things along with the programming style and programming strategies. Inconel, tungsten, and stainless steel alloys, they are very typical materials. Basically, they have got high strength, especially Inconel. It's got a pretty high strength, corrosion resistance. Some of these materials are age hardenable. That means keep them for a longer time, they start hardening up. High heat resistance, and they are also pretty stable. For example, Inconel is having a very high heat resistance, and it's pretty stable at very high temperatures, close to 1,000 degrees. It's pretty stable. It can withstand a lot of heat. Now, because they have this high heat resistance, it also means that they have got very poor thermal conductivity. Now, this is one of the reasons why machining such materials is really difficult, is the conductivity of heat. Inconel, for that matter, has got a rapid work hardening tendency. So if you're not careful with your parameters, if you're not careful with your lubrication, after the first cut, you could be inducing work hardening into the material, and then the subsequent next cut becomes very difficult to take. Tools just chip off, they just burn out while cutting Inconel. And obviously, putting all of these things together, they have poor machinability, except for aluminium. Most of these alloys have poor machinability. Now, in the diagram on the right-hand side, you could see that the specific strength of the material decreases as the temperature goes up. Now, the temperature can be pushed up by pushing up the cutting speed. You can push up the cutting speed beyond a certain limit, and the temperature will start increasing, and the strength of the material will drop, and that makes it much more easier to cut. So if you look at the graph itself, aluminium, of course, is the easiest of the cut. The next one, surprisingly, is titanium, because titanium has got much lower strength at much lower temperatures than steel. And the most toughest material to cut, in spite of dropping off a bit of their specific strength, is the nickel alloys, basically Inconel. So we are going to spend some time on how to cut Inconel also. The challenges that we are facing today in machining these materials are basically chip thickness variation. Now, this comes because the program or the code that is actually running the machine is not smart enough to realize that it needs to have a constant cutting load. Thereby, it keeps varying the engagement into the material, and this difference in engagement causes the chip thickness to vary while keeping the feed rates constant. High heat stress, because you're cutting materials like Inconel and titanium, the heat generated is very high. Tool wear also is very high. This is one of the biggest challenges people face when they are cutting titanium or Inconel, especially Inconel. Tool wear is very high. You have got edge buildup because of the plastic deformation of the material. The material starts sitting on the edge, and thereby it starts chipping off. Low thermal conductivity, and that's because the heat generally when a material is cut is carried out by the chip that goes out of the material. But in these materials, especially Inconel and titanium, being poor thermal conductors, the chip or the material does not carry the heat, but the entire heat is passed on to that feeble edge, the cutting edge. So the geometry of the tool also makes a big difference in the way you cut Inconel or titanium. The other changes are like the deformation, especially you have to be very careful so that the part doesn't warp. So getting your cutting conditions right is really a major challenge when you're cutting these materials. Now, if you look at the machining process itself, there are several things that influence the machining. First of all, the machine, the power of the spindle construction, the rigidity of the machine, the rigidity of the axis, and what control you're using on it. These factors affect from the machine side on our machining. The other thing that influences the machine is the cutting tool itself. What grade of carbide? What is the tool geometry? How are you holding the tool? What is the helix angle? How many flutes? There are several things from the tooling side that also affect machining. The other important aspect here is your work holding itself. If you have poor work holding, you cannot be aggressive with cutting. You have to drop down all of your aggression and go with a very, very low or moderate level of aggression. But if your holding is extremely good, like in shunk kind of holding devices, where you hold very less and it has got a really high force of clamping, you can be more aggressive in the cut. And sometimes aggression can actually increase your tool life in case of materials like Inconel. You also have the coolant. There have been several experiments that have taken place on having everything perfect, and there are experiments that have concluded that a cutting fluid or a cutting lubricant, fluid lubricant with 8% cutting oil mixed with demineralized water can give extremely good tool life. Even varying the percentage of the oil in the demineralized water can make a big difference. So if you go from 8% to 10%, the tool life almost drops down to about 25 to 30%. And if you drop down the cutting fluid percentage in water from 8% to, let's say, 5%, the effect is the same. You almost drop to 30-40% of the tool life. So you need to get the concentration of oil in demineralized water correctly when you're cutting such tough materials. So coolant also plays a very, very important role. From our side, we have no much control of the machine, the tool holding, the coolant, or the work holding. But what we have is we can greatly influence the creation of cutting conditions and adhering to the cutting conditions using a program called iMachining. So you have to understand what iMachining is all about. iMachining basically is a revolution in CNC machining. It's the next step after CNC was born, because it has completely taken over the CNC world by storm, basically because it's an out-of-box solution. It doesn't go by the conventional rules of machining, but it's completely out-of-box, but yet adhering to the basic principles of milling. These features are like productivity increase and time savings by shortening the cycle times by 70% or more, dramatically improving the tool life. I'll explain to you how the tool life goes up, because we have got documented evidence that the tool life goes up dramatically. It's said in iMachining that the harder the material, better is the performance of iMachining, and it's true that we have seen, in part with our own eyes, that the performance of iMachining exponentially goes up when you cut really hard materials. Now, one of the biggest things, or one of the features of iMachining is its ability to handle small diameter tools. Now, you would have seen in other softwares, they also talk about toolpaths similar to iMachining. But you must have noticed one thing if you observe closely on all the videos that have been put on YouTube and other places of other systems. You will notice that none of them really talk about tools less than 12 diameter or 10 diameter. Nobody talks about 6 diameter, 8 diameter, 4 diameter, 2 diameter. That's because when you go down on the diameter of the tool, you have to be dead accurate with your cutting conditions. Because if you're not accurate with your cutting conditions, these tools they don't have high strength like 12 diameter or 16 diameter, where a bit of variation in your cutting conditions can still make the tool perform. Here, if there's a change in the cutting conditions, or the cutting conditions are not suitable, the tool just breaks. So iMachining excels when the diameter of the tool goes down, because it can generate a pinpointed accuracy of accurate cutting conditions. Very high programming productivity. It's just a 4-step programming process. You define the machine, material, tool, geometry, and you're ready to go. Shortest learning curve in the industry. We have got our training times of less than a day when you want to learn iMachining. So it's not more than 1 day to learn iMachining. And the most important part, or the most beautiful part of iMachining is its technology wizard, which is a patented technology nobody else can copy. And this technology wizard comes up with optimum feeds and speed, taking into account the machine, the material, the tool, and the geometry. Taking into account all of these things, it generates a very unique set of cutting conditions. And these cutting conditions are so accurate that you actually don't need to go and do any trial and error on the machine. Very first time, whether you're cutting aluminum or whether you're cutting Inconel, you could achieve the first time right product. You don't need to go and do trial and error to see if the feed is working or not. So, iMachining basically has 2 things in it. One is the intelligent toolpath generator, which generates these unique patterns of toolpaths. And these unique patterns ensure constant mechanical tool load. Okay? So the first word for us is constant tool load. And then it also has a second component, which is a technology wizard. And this technology wizard calculates the cutting conditions for a given machine, for a given material that you're going to cut, for a given tool, and for a given set of geometry. You change any one of these, the cutting conditions are updated automatically by iMachining. So both of these generate a very intelligent toolpath, which has got a very unique pattern, and the pattern follows those set optimal cutting conditions. So in the end result is that you get a very intelligent toolpath, which is ready to run on the machine. If you look at the difference between iMachining toolpath and standard cutting toolpaths that you see in CAM systems, the standard cutting toolpaths have the philosophy of using a traditional step-forward principle, where they take the outermost boundary and keep collapsing it by offsetting it until it reaches to the center and it cannot be offsetted anymore. And this offset is based on the step over that we define. Now imagine your tool, okay, on this particular path here. When it gets to this particular path, or worse condition, when it gets to this path here, the tool, as you see here, is completely engaged, more than 180 degrees. Now imagine if you're taking a big depth of cut and you're engaged the tool more than 180 degrees, the amount of cutting force that is there on the tool is going to be tremendous. That's why when I say that iMachining excels when you're using a smaller tool when cutting, is that when you cannot control your tool load, and if you're using a smaller diameter tool, you're going to break the tool straight away, because the force acting on the tool is so high that your tool will just chop off. Okay? So in order to avoid this situation, what people do is they distribute this depth of cut into several depth of cuts. So they take shallow depth of cuts and then they try to go faster. This is what the philosophy of high-speed machining was altogether till this time. This is what has been propagated to us all this time. Shallow depth of cut and high feed rate. iMachining is about to change all that. So in order to overcome such situations, we have a very convenient solution wherein we drop the feed rate, or rather we calculate the feed rate, what should be there on the process, and apply the feed rate for the entire process, thereby slowing down the entire process. Or we go to the next route, which I just explained, shallow depth of cuts and high feed rate. Okay, works fine when you're using inserted cutters, but doesn't work when you're using the solid carbide hand mills, as it basically cuts down your cutter life, because your tool is going to get worn out only in the front and a bit on the diameter, not over the overall length. So that makes the tool go to the regrinding more often, and it's not just reground on the diameter, it's also chopped out because the front has already worn out. So they remove 3-4 millimeters, regrind the front again and send it back. So effectively, we're shortening the tool length, and at one point it becomes useless. So your life of the tool, what it would have come up, does not live up to that life. Okay. So iMachining overcomes majority of the problems what the conventional tool paths are offering you. First of all, it generates smooth tangential tool paths. So even when there's a change of direction, it's pretty smooth. It doesn't put any kind of load on the axis. So the tool paths are always tangential. We have another patented product. We have another patented technology, and that is controlling the step overs. We have a minimum and a maximum step over based on the engagement of the tool with the material. So, okay, so if the engagement is more, you will see that the step over is more there, and the engagement is less, the step over is less. Now, based on our step over and engagement, the feed rate are calculated. So if you have got more engagement or a bigger step over, the feed rates drop down. If the engagement reduces, the feed rate goes up. This is done to ensure that you have got a uniform cutting load, or my chip thickness is going to be uniform throughout the cut. It doesn't matter if you're cutting a straight line or an acute angle. My chip thickness is going to be the same. We also have exact stock machining. That means we precisely know how much stock is remaining and where is it remaining. Okay, so we don't just go and cut air, but we precisely know where the material is remaining, and we cut exactly the stock. So if I have to sum up the features of iMachining, it's got unique tool path pattern, like what you see out here. Unique pattern, and it's got constant cutting force based on engagement angle. It varies the engagement angle, thereby dropping or increasing the feed rate, maintaining constant chip thickness. optimum cutting conditions by generating optimum cutting conditions based on machine, material, tool, and geometry. And the most important thing is vibration control, where we can predict, even before the machine is started, we could predict what kind of a chatter are we expecting in this entire process. And we also have ways to avoid it, which we're going to see soon. Now, how did iMachining start all of? I mean, many people, when I explain iMachining to them, especially the cutting tool people, when I explain iMachining to them, I can explain to you. Excuse me. Sorry. I was explaining to some of the cutting tool vendors about iMachining, and they came up with this statement saying that we generate a very high VC and our cutters are not suitable for such a high cutting speed. And that brings me to this slide of Solomon's theory of high-speed machining. If you remember a couple of slides back, I was referring to low depth of cut and high feed rates. This is exactly going to be the other way around. Solomon was a German scientist. In 1931, he was conducting these experiments on aluminium, and he was plotting a graph. If we go to our tooling friends and ask them about how the temperature rises with the cutting speed, we could easily plot that on our graph, whereas this is our VC and this is our temperature. Okay? So as our VC rises, temperature also goes up. So generally they explain to us that there is a linear curve. Solomon found something different. He also had the same phenomena where he calculated that as he increased the VC, the temperature started going up. So he kept on pushing the VC higher and higher. A point came when the temperature no longer started increasing, so it was actually not changing at all in spite of the cutting speed going up. He pushed it further, and a point actually came when the temperature started dropping down. So if I take a VC here for temperature, this is my VC. This point is going to be about 4 to 6 times higher than the conventional VC. So if you are going to push your cutting speed 4 to 6 times more than the conventional process, conventional VC, you are going to end up with a similar cutting edge temperature. Higher VC means higher feed rates. Higher feed rates means shorter machining time. But the problem starts there, that you could push your VC higher, you could push your feed rates higher. But if you are unable to control your engagement of the tool into the material, you could end up with a catastrophic result. You could end up breaking the tool straight away. So on one side, we use Solomon's theory to the core inside iMachining. On the other side, we also make sure that we generate, in conjunction with this theory, an optimum condition. We don't say we straight away jump 10 times. No. It could be anywhere between 6 or 7 times. We go within the range. And that basically is how we generate the cutting conditions, which are then applied to iMachining to generate these unique tool parts. All right, let's move further. So if you look at the slide here, you can look at various materials on where the transition range or the conventional speeds are and where the iMachining ranges are. For example, we're talking about steel, titanium, and nickel alloys. For example, Inconel. I could give you an example of Inconel because we've done this few trials where the cutting speed generally given by tooling manufacturers. They have a certain goal on tool life and the cutting speed. So for example, a 16 diameter or 12 diameter cutter with a VC or cutting speed of about 40 generates a life of 28 minutes on Inconel. We moved it up almost to 122 here. So iMachining generated a VC close to 122, more than this range. Okay, that was about 3 times. So the general thing is, if I push the VC so high, will my tool withstand a material like Inconel at that high VC? Would I get tool life? The results were dramatic. From a 28-minute life, we went up to 86 minutes for the same tool, for the same material, Inconel 718. So we pushed the tool life to more than 3 times, 300%. And it's not magic. Okay, there is a lot of science behind this, and I'll explain to you why my tool life goes up even when I push the VC 3 times. The whole process, okay, of let me go back again because it's pretty interesting to come back to this figure where I explained to you that at 4 to 6 times of this VC here, this is that 4 to 6 times, 4 to 6, I get a lower temperature, okay? Because at 4 to 6 times, if I had to really trust my tooling guys, this would have been my temperature. But actually my temperature is much lower. So what is causing it? That can be best explained by this slide. So this basically is explaining to us the balancing, the temperature balance process. When the first contact of the tool happens with the material, the cutting edge temperature rises. When the cutting edge temperature rises, the material starts transiting from solid to plastic phase. When it is in the plastic phase, the cutting forces to cut that material is brought down. So you have the material is in the plastic phase, cutting forces required to cut is much lower. Because my cutting forces are reduced, I expend less energy. I spend less energy to cut. Now, because I'm spending less energy to cut, I'm producing less heat. So you see, Solomon was right when he said when you push the VC to 4 to 6 times, you're actually producing much lower cutting edge temperatures. So your heat produced is much lower, and when your heat produces much lower, the cutting edge temperature actually goes down. And within a split second, it goes into an equilibrium where your temperature is always low at that high VC. So temperature rises, transition to plastic phase, cutting forces are reduced, less energy is expended, less energy expended, less heat is produced, less heat produced means my temperature is down. Now, there is a condition to this, like they put an asterisk mark and say conditions apply. There's a conditions apply to this. The condition here is you must have a pretty good lubrication system. If you're cutting steel, you need to have good air. If you're cutting sticky materials, you need to have good fluid lubricant. So we are talking about if you have got that condition right, then this process fits in perfectly. Solomon's theory fits in nicely, and you actually cut faster at a higher feed rate and a much higher cutting speed. iMachining, like I said, works on the principle of constant cutting force. And the constant cutting force is derived or generated by managing cutting angle or a section of the tool engaged with the material. So we have got a minimum and a maximum cutting angle, and iMachining keeps the tool between the minimum and maximum engagement angle into the material, and thereby it drops or increases the feed rate to maintain constant cutting load. And this we are talking over the entire cutting length, the flute of the tool. Because of this process, because of this philosophy, we can use small cutting tools. So if you go to YouTube, you'll see a lot of videos done with 2mm end mills on really hard materials, which perhaps you would not see with other systems which claim to have iMachining kind of toolpaths inside them. Like I said, when you have different engagement angles, and if you would like to keep a constant chip load, now as the engagement angle differs, for example, if you have a minimum engagement angle of 20 degrees, you have got a certain feed rate. Now if that engagement angle goes up, let's say it goes up to 60 degrees, in order for us to maintain a constant chip, I have to drop my feed rate. So iMachining intelligently increases and drops down the feed rate based on the engagement the tool is making with the material. Okay? And thereby it generates a constant load on the tool. And if you go to any tool manufacturer, they will always say, my life of the tool is estimated at a constant cutting load of so much acting on my tool. So if you are going to vary the tool, load on the tool, you're actually going to reduce your tool life dramatically. Okay. What are the peripherals that influence the machining of such materials? The first one is definitely the cooling. Should I go with fluid? Should I go with air? If I go with fluid or air, how should be my construction? So there are 2 points within the fluid design. The first one is the choice of lubricant. The second one is the design of the lubrication delivery to hit the tool point when it's cutting. The other next important thing is the cutting tool itself. What should it be? Should it be a sharp corner end mill? Should it be a chamfer end mill? Or should it be a bull nose, the radius end mill? The tool holding is very important here because with iMachining, we have very high axial loads. So your tool holding must be really rigid. So whether to use collet, whether to use hydro grip, whether to use power chuck, that is the decision we need to make in the next few slides that we'll see. Work holding, whether you're going to use mechanical wise, hydraulic wise, or work holding fixture. These things also influence greatly the machining and the machining conditions. Cooling, it plays a very important role, especially when you're cutting Inconel and titanium. First of all, we did a lot of cutting with Inconel and titanium with several of our customers and tooling vendors, and we realized that if we want to have a very good tool life, the first important thing is to have high pressure coolant. So if you're cutting titanium, if you're cutting Inconel, or if you're cutting stainless steel, you must always use fluid lubricant, okay? Because these are sticky materials. And the goal here is to throw the chip out and, more importantly, cool the tool because the heat is being passed on to the tool. If you're using air for steel, because for steel we recommend air, okay? If you're using air, direct, if possible, cool air. If not, even the room temperature air is good enough. And this is a must for steel. We're talking about anything beyond 45, 50 HRC, start using air because In steel, it's just exactly the opposite. The heat is not actually being passed to the tool. The heat is being carried away by the chips. So if the chip remains in contact with the material of the tool for a longer time, or a longer period of time, it's likely that it will pass the heat. So the moment a chip is generated, it must be evacuated. And the best way to evacuate that is to use air, right? So for steel, air. Various steps that were conducted with different cutting to fluid manufacturers, cooling fluid manufacturers. The conclusion was reached by some of the top cutting fluid manufacturers that when you're cutting titanium, when you're cutting Inconel, or even stainless steel, 8% of 8%, that's the concentration in demineralized water, gave extremely high tool life, almost more than 50% than what you would probably use, either 10% or 5%. 8% was an excellent concentration. As far as delivery of the lubricant when you're machining Inconel, titanium, or stainless steel, the delivery of the coolant or lubrication is very important. Now, if you're having, let's make another drawing on the slide itself. Let's say I'm having a block, okay, and I have this tool. The tool is going to move all around. Simple. So, if I have a regular cooling system where the coolant is hitting only from one side, it's fine when it is machining on this face and it's machining this face. But if it's going to go here, okay, and the tool is here, this fellow cannot hit because it's gone into a shadow region. In such cases, you need fluid also coming from this direction. So we already have two directions. If you ask me, the best possible way is to have fluids hitting the tool from 4 different directions. Okay? This is the ideal scenario. The best case scenario is right here explained on this ring. This ring is attached to the spindle arm. You have got an inlet and you have got nozzles coming from every different directions. So you actually hit the tool from different directions. Thereby, you're making sure that you don't end up in any kind of a shadow zone when the tool is cutting. Okay, this is very important because if the tool misses or the coolant misses to hit the tool, you're actually damaging the tool more than not putting coolant at all. So you have a coolant that is going into a stop-start condition. It goes into the shadow region, it's not hitting. It comes back again into the positive region, you get coolant. Again, it goes into the shadow region, no coolant. This should not be the case. So the ideal situation is to have a ring kind of a cooling system. Now, from what I know, this ring is available. I checked up on the web. It is available for, I think, for $8 or $10, and it can be bought online. And these are modular structures. So depending on your size of the spindle, you could order 1, 10 or 15 or 20, and then just attach them and create this ring. And each of them can be moved up and down, so you can hit exactly the right spot when it's cutting. So the cooling makes dramatic difference to your cutting. Cutting tool, we suggest that when you're trying to cut Inconel or when you're trying to cut titanium, you need to use as big tool as possible. Of course, if the geometry doesn't allow, then there's no way you could use a bigger tool. But if the geometry allows, you'd always suggest you to go with a higher tool because that has got more strength. We suggest that you use a cutting tool with a corner radius. Okay, we have seen that sharp corner tools increases chipping because the force that is acting on that very small area is very high. So generally, in the very first contact, you can see that it will chip off. And why corner radius? Experiment done with Sandvik, they have found out that tools with corner radius give you much higher tool life than with tools with chamfer. Okay, we never considered tool life with sharp end mill because generally they don't survive. The other very important thing when you're cutting Inconel or when you're cutting titanium is that you should insist on tools that have honed edges. Very fine honing is done on the edges so that the edge is not sharp, but it is blunted to give you a very fine radius. This radius gives great strength to the tool, and the tool life jumps up dramatically. So ensure that your tools are honed and not just ground sharp. Tool holding, we just do not suggest the use of collets when you're machining tough materials. When you're machining aluminium, in some cases it's okay because smaller diameters, collets are fine, but tough materials, stainless steel, if you're cutting Inconel, if you're cutting titanium, collets are completely a big no. We will suggest you to use hydro grip, power chuck, or shrink fit mechanism to hold the tool. First of all, they minimize the runout, and that increases the tool life. It gives great stability for cutting. There are no vibrations that are induced because of poor holding. And because of high clamping forces, they help to prevent pull out of the tool, especially when you're using iMachining, because in iMachining, like I said, the action forces are very high. So tools can be pulled out if you're using collets. And for every 10 microns in added runout, the tool life goes down almost by 50%. This is not me, I'm telling, but this is a statement by majority of the tool vendors. When you ask them, what difference does a hydro grip or power chuck do on the tool life? So this is what they say. It reduces the runout, and reduced runout means higher tool life. The other important thing that you need to do inside iMachining basically is that you need to decide the feed rate control on a corner or going over an arc. Now what happens, it's pretty simple. Again, let me explain using some simple curves. Okay, this is my edge and my tool is rolling over here. Okay, this is the direction the tool is going. Now this point here is a very small area. Okay, and if the tool is here and the tool is here, okay, this is point 1 and this is the next point. However, when I extrapolate this point to the radius, it actually has to travel a much bigger distance in order to move over this small point. Now, in order to do that, you can imagine if this feed rate here was 10, I'll have a much higher feed rate on this line because it needs to traverse the same distance, or rather the higher distance, where it needs to increase its feed rate. Okay. Now, when it's doing external corners, it's fine. Just imagine what would happen for the internal corner. You can look at the figure out here. If I keep the constant chip thickness at 0, what is going to happen is that when it goes into the corner, okay, it tries to keep the same feed rate, right? So the edge, the tool, the peripheral feed rate goes up because of this phenomena here that I just explained. It needs to travel a bigger distance. So in order to travel a bigger distance, the machine pushes up the feed rate, right? So what you're having is that if you had a chip thickness of 0.1 when it's going over a straight line, we would end up getting a chip thickness of 0.2 or more when it's going on the corner. Now, this goes against the principle of iMachining, which we say that there's a constant tool load that we have to maintain. So in order to overcome this, we have got a slider inside SolidCAM that allows us to control the chip thickness. So if I keep it at 100%, what iMachining will do is, when it goes into the corners, it will drop down the feed rate to such an extent that it will try and maintain the FZ value even when going over the corner. Okay? It will not push the feed rate, but it will drop it down so that it tries to maintain the peripheral feed rate in such a way that my FZ is not affected in any way. So I keep the chip thickness constant when I'm going over the corner, and the moment the corner is over, it returns back to its original feed rate, right? So the slider must be always set to 100% when you're cutting the tough materials like Inconel, titanium, and stainless steel. If you're cutting, let's say, aluminum, you can keep the slider even at 0. You can let it go at the same feed rate, get a higher chip thickness, it doesn't matter. Okay? But for super alloys, for titanium, for the stainless steel and all, you need to have the slider set at 100. Okay. The other important thing we need to figure out is that, in spite of all these things that we specify inside iMachining, what we forget is, excuse me. What we forget is that these are all theoretical values that we take inside iMachining. For example, iMachining needs us to define the tensile strength, the ultimate tensile strength of the material. It needs us to define the machine properties, everything. Now, these are theoretical values. Especially the machine characteristics, the material characteristics, they are theoretical values. So we need to first determine, especially when you're cutting Inconel and titanium, because this can dramatically alter your tool life. Let's say you've got a block of material from your customer, which is, let's say, stainless steel. And I would like to get the exact cutting conditions to cut that particular material. So first, I need to determine the machinability of that material. What is machinability? It's basically a term that indicates how the work material responds to the cutting process. And we have a mathematical formula for that, where Km is the machinability index, V60 is the cutting speed for target material that ensures life of 60 minutes. And then there's a reference material that ensures to life of 60 minutes. So if the Km value is greater than 1, then the target material is better than the reference material. If Km value is less than 1, it means that the target material is or has poor machinability than the reference material, vice versa. So how do we calculate the machinability? So you have got, let's say, an AISI steel of which has an index of 1. This is our reference value. Machining this steel at 0.5 meters per second gives us a tool life of 60 minutes. Therefore, our V60R is 0.5 meters per second. The machinability index for stainless steel 302 is Km, that is 0.23. That is, if I machine stainless steel at 0.23 meters per second, it will give me a tool life of 60 minutes. So my machinability is 0.23 divided by 0.5, that's 0.46, which means the machinability of SS302 is lower than AISI 1112 steel. For AISI 1045, it's 0.36. So the tool life of 60 minutes is achieved when my cutting speed is at about 0.36 meters per second. So the order of machinability, it would be AISI 1112 first, AISI 1045, and then SS302. That's how the machinability is determined. But for us, the machinability has to be determined in a completely different way, because these are all theoretical ways of calculating machinability. We can't depend on theory, but we have to go down to the shop floor to determine the machinability before we start cutting iron machining. Why is it so important that you determine machinability, and why not just go with a theoretical value, or for that matter, the value given to us by the material supplier? Because every material supplier, when he supplies a batch of material, gives you a test chart, and the test chart gives you the value of the UPS. So it's important to understand why machinability is so important. First of all, it improves your tool life dramatically. Trust me, you've seen that changes like even 10% difference between what machinability was there with the test chart and what we determined improved the tool life almost by 60%. It allows iMachining to better decide the exact cutting conditions. So it gives it much more accurate picture of what material it's trying to cut. Better cutting conditions result in a better surface quality. And in materials like aluminum, when you're cutting large parts, frame parts of aluminum using iMachining, it reduces the chances of warpage because you're getting very close to the exact cutting conditions. And it basically improves the overall process. Now, like I said, why we just can't simply stick to what is the value that's being given to us by the material supplier? Why do we need to go to the shop floor to determine machinability? The structure of the material itself, microstructures, the mechanical strength, hardness, hot hardness, strength, work hardenability, thermal, all these things are influencing the machinability. The level of process parameters also influence the machinability. The cutting tool material also influences greatly the machinability, and also the machining environments, cutting fluid application, work holding, etc. They also affect the machinability. So what we do basically, and this is something that we tell every customer of ours, to determine machinability, especially when they're cutting SS, titanium, and Inconel, to take a sample block. And what we did here was just to explain to you how it works. We just taken a sample AISI steel, 100 by 75 by 50. We made this step, and the step depth is 24, and the width of that step is about 10 millimeters. We are using a 12 diameter end mill, 4-flute, 45-degree helix, and Mazak FJV machine with 10 kilowatt spindle. So we go first to the material supplier or to MatWeb to find out what is the tensile strength of this particular material. Define that in iMachining, and we generate a tool path at level 8. This is the highest level inside iMachining. We generate the highest MRR, material removal rate. We generate the tool path, but we have to ensure that we get ACP. Now, what is ACP here? So ACP is pretty important. Again, let me make a drawing. Now, what is ACP is that my tool is in contact with the wall. My tool has a diameter, and it has helix and number of flutes. Okay, ACP is basically the contact points the tool is making with the wall. Now, if you have whole number, like in this case 2, if you have whole number, it means the forces are acting only in one direction, which means that I'm going to have a very stable cutting. But if I get this value as 2.6 or 2.4, it means there is one point that is floating, okay, where the forces are acting in every direction possible. Now this causes unstable cutting, and unstable cutting straight away causes vibration, and the vibration straight effect is shatter, and sometimes you could end up damaging the tool. So it's important that we, for the sake of testing, at least generate a whole number of ACP. So we are not going to go to 24, but we stop at 19 millimeters where it generated a whole number of ACP. We know that it's going to be a stable cut, so the readings that we are going to see on the machine are going to be accurate. Okay, so we note down these values. You note down that the power required for cutting at this tool path on the machine is going to be about 5.2 kilowatt or 52%, because we're using a 10 kilowatt spindle, so it's 52% of the power. That's what iMachining is suggesting that's going to come up. We generate the tool path, take the G code, go down to the machine, and we run the machine. After the first 2 passes are done, because generally the material might have some variations, after the first 2 passes are done, we start observing the spindle load meter. Okay? Till the machining is finished, we'll note the spindle load meter. Assume in this case, we get a spindle load of 60%. The spindle load meter is showing 60%. We just note down that it is showing 60%. We come back to our system. But as per the UTS that we defined, 515 megapascals from MacWeb, we should have had 52% load, but we're getting 60% load. That means this material is slightly more tougher than the UTS, what the UTS is suggesting. Okay? So now we need to arrive at the exact machinability of this material. So what do? We go back and we have a machinability factor inside when we define the material. We push that down to 16%, okay, roughly 16%. We save and exit, go back, and we put down the same conditions again, the same cutting angle, maximum, the same maximum VC, and the same maximum chip thickness, because this has to be the same what it was before when we started cutting. Okay? So when we put that, we immediately get the power, which shows that we are going to get 6 kilowatt. Now, the moment we are close to what we see on the machine, you can be assured that this is the machinability of that material, which was not 0, but it is minus 16. That means the material that's come in this batch of, let's say, 200, 300 blocks is having a machinability which is 16% tougher than the material, a reference material that we got from the web. Now, what this does basically is this gives iMachining a greater accurate picture of the material to come up with accurate cutting conditions. Okay? Remember that this particular test has to be repeated if there is a change in either the batch material or if you're changing the machine. Okay? Because the machinability can vary to a small extent, but mostly it is done when the batch of material changes. Like you have one batch of 200 blocks, you machine it completely, you get another batch. Probably it is taken from another billet. So you need to run this test again to figure out what is the machinability of this particular block. Remember, we are not changing the UTS, we are only changing the machinability, because UTS doesn't always give you the complete picture. Okay, we'll come back to this particular example in a moment. Just go into iMachining, and I have got this nice block out here. Now this is a mold part, and I would like to rough this out. Now the stock is basically a block. Okay, we're going to cut it out from a block. Now, before we start machining using iMachining, it's very important to understand what iMachining should be used. Should we use the 2D? Should we use the 3D? Okay, so it is very important for us to understand what kind of iMachining we have to use. Generally, the philosophy about all programmers is that if it's a 3D model, let's just dump 3D and let it do everything. But if you're a smart programmer, you'll probably analyze this part and say, hey, look, there are several areas in this that can be done with iMachining 2D. And we know that in iMachining 2D, it doesn't care about scallop and other things, just is used for volume removal. It's very fast. So the first thing that I generally do when I get a part is I check what is the draft available on this tool. I see there are several areas that are having straight walls or no draft at all. So basically what I can do here is I can straight away apply iMachining 2D. So what I'm going to do here is I'm going to add a milling operation, iMachining 2D. And let me pick, I already have the contours defined. So I'm going to use one of these contours. Okay. And I'll pick the tool. I'm going to use a 16 bull nose with corner radius 3. Now, Again, I'll go back into our evaluate and check for the curvature. You can look at here that curvature is 3. The general principle here is to use a tool that is more than 3 or exactly 3. I could use even corner radius of 2, but for hard materials and tough to cut materials, the corner radius should be bigger. Bigger, the better. Right. So what I'm going to do here is I'm going to pick 16 bull nose, corner radius 3. You can see that the tool outside holder is only 16. Now this is a thing that I need to take care of. I can't go to pocket depth here. This is 70. I can't use this. I'll have to stop it at 55 millimeters. That's one drawback of iMachining 2D, that I need to define my depth. But the pros outweigh the cons straight away, so I'm going to go ahead with it. And I'm going to use level 6 straight away. You can see that it's just using 4.5 kilowatt, which means this machine is 15 kilowatt. I have got great amount of leeway with me. I'm going to keep it at that. I would like to keep a stock of 0.3 millimeters. Okay, and let's change this to 8 millimeters. That's half of the tool diameter. And let's hit save and calculate. Okay, this tool path is calculated. It's pretty quick. It doesn't care about your scallop. And if I run the simulation, you can see that it just opens up on a steel of 35 HRC. The time taken to cut a slot of 55 millimeter is about 9 minutes. Very quick, very fast. Okay. Similarly, I have got one more area here and another area out here. So I can simply copy this tool path, or I already have got a couple of these tool paths here, so I'm going to copy them and paste them below here. Okay, and hit calculate, because this is going to machine this pocket here. You can see that it's already generated the tool path for this area. So let me simulate, because these are straight walls, so I can quickly generate with iMachining 2D, and then I could apply for the remaining areas. For example, 2 minutes 40 seconds. This is opened up. Okay, and the next one is for a small area here. I'm using a different tool. Okay, so I have opened up in a matter of 11 minutes. Majority of areas, the big areas are already opened up. What remains now is a smaller area which has got a lot of contours. So there I'm going to use iMachining 3D. So I'm going to calculate that in parallel, or just put for calculation, and then we can move to the next slide. Okay, while this is being calculated, which is obviously going to be pretty quick, so we are not going to see the entire process. Let me go back to my presentation ahead. iMachining forces on spindle and axis. Why do we say that we have got, or rather iMachining generates very high tool life? That's because the load on the tool is constant. And you'll be surprised to see that the load on the tool is much lower than what the load would be on the tool at 1/10 the depth of cut. And this is something that's been measured practically on the machine using several equipments. The iMachining tool path, combined with the optimum cutting conditions provided by the technology wizard, which I showed you, it ensures constant load on the tool in any situation. The iMachining makes sure that your tool sometimes is, when you're cutting steel and aluminum, it will be always loaded between, or rather when you're cutting steel, basically aluminum can go higher. is between 4 to 17%, depending on the level of the slider used and the material you're cutting. Several machine tool companies concluded that the force acting on the spindles are the smallest of any CAM systems that are using similar kind of tool path for high-speed machining or high-performance machining. Hermle concluded the same. Makino concluded the same on A55 and A61 machines. However, the proof of the pudding comes from the fact that this whole process is documented, is measured in a lab. We have this was a cooperation with a university in the Czech Republic, and it was focused on cutting force measurement. The university is equipped, along with their CNC machine, is equipped with rotational cutting force dynamometers to measure the force on the tool, axial dynamometers to measure forces on the axis, and the workpiece dynamometer to measure force acting on the material. So you have got the rotating dynamometer, which is measuring the force acting on the spindle, basically the tool. And then you have the axial dynamometer that's measuring the force during drilling and milling on all the axes on the machine table. And then you have a workpiece dynamometer, which is basically measuring the force in all directions on the workpiece. The data is transferred by shielded wire. The PC is equipped with a measuring card that receives the signals from these dynamometers, and each component is processed separately. The spindle is processed separately, the axis is processed separately, the workpiece is processed separately, and they use the software LabVIEW to measure the forces. The sample part was a simple pocket with an island. Material cut was aluminium, 8mm diameter end mill with 3 flutes, cutting length 30 millimeters and a helix angle of 38. iMachining level was 5, which is considered moderate aggression. It's not very aggressive. And these are the cutting forces in iMachining. The yellow forces are basically the ramp when the tool is ramping, and the green is the machining forces. You can see that it was about 270 odd at a depth of cut of 30 millimeters with a VC of 283, RPM of 11,250, and a feed rate of 4,000 or 4.5 meters, or FZ of 0.13 per tooth. Then they measured the conventional pocketing strategy. Depth of cut 4 millimeters, side step 7.2, feed per tooth 0.09, and the feed speeds were set according to the manufacturer's catalog. By the way, for iMachining, the technology wizard determined its own iMachining feed rates. How does this behave with conventional pocketing strategy? How does the forces behave? These are the forces with conventional classical pocketing condition when machined at 4 millimeter depth of cut. That's the average. So we're talking about close to 470, whereas for iMachining, they were somewhere here at 8 times the depth of cut and almost 3 times the feed rate and almost 4 times the cut and speed. The forces of iMachining are much lower than what you expect or what you get in conventional cutting. Now this is well documented, and this is one of the crucial reasons why the tool life gets dramatically extended even when you're cutting tough materials like Inconel and titanium. That's because force acting on the tool is much lower. We determine optimal cutting conditions to ensure that we generate a constant chip load on the tool, thereby dramatically improving the tool life. We also have done a lot of experiments with different cutting tool vendors, and one of them was Metal, where we generated test results for machining stainless steel P660 and titanium TIAL6B4. It was a simple geometry, but gave us great in-depth of what iMachining could do. 250 by 200 by 60, simple stainless steel. Roughing was with 16 R3 bull nose tool. Depth was cut 23 millimeters, and VC 171. The suggested VC by Kennametal was about 102 for this particular part. And finishing was with 16 R3 bull nose again. Here the VC was 205. The finishing was done at level 6, which is pretty good aggressive level. And it's almost twice the VC of what Kennametal suggested. Cycle time for roughing and finishing, 3 minutes 36 seconds. The pocket was done again using the same tool. Again, similar results. The pockets finished with 4 minutes 48 seconds. Titanium, a block of 200 by 175 by 50. Cutting diameter 16R3. VC 83. Remember, the VC here for titanium generally suggested in the range of 40 to 45 to 60. And at level 4, that is the medium aggression, we still have 4 notches to go up. The cycle time here for outer periphery machining was 3 minutes 18 seconds. Internal pocket 4 minutes 42 seconds. The load on the spindle 20%. The second pocket that was machined, it was machined using 12R.8, VC of 113, and the cycle time was 3 minutes 58 seconds. What's more important here is the tool wear, because they were really not bothered about the cycle time. We knew that cycle time was going to be lower than conventional cutting. But what is more important here is how did the tool behave during this entire cutting? The diameter 12 tool that was used majority for the part, we observed a wear of about 0.1 millimeter on almost all cutting edges, which is very good when you're considering the fact that you're cutting these tough materials. Okay, you can see that they're almost uniform kind of a wear that's come up on all the edges of this particular tool. Few success stories around the world. We've got a customer cutting titanium. Standard cutting time was 17 minutes, down to 3.5 minutes a piece. Saved 80%. We did another trials with ISCAR here in India, and it was an Inconel 718 on a Herco BMX 50, diameter 16, chatter-free end mill, and the suggested VC by ISCAR was 45. iMachining at level 4 generated 81. The ISCAR's estimated tool life was 26 minutes. iMachining achieved a tool life of 86 minutes for this tool, for this material. Okay, so it was dramatically almost 3 times tool life. Burns machinery from 75% savings. This is a customer for oil field equipment, savings of about 86%. Again, they machine titanium and Inconel. And then we did a trial with the most hardest material available to date, tungsten carbide. What our competitors were doing was doing it in 42 hours with 9 tools, and iMachining did the same part in 54 minutes, just single tools. So you can dramatically see the difference. Number 1, on the time. Number 2, on the amount of cutting tools that you save when you're cutting these tough materials. Okay, let's go back to our part and see. Okay, we've done, it's generated. Let's run the simulation. Let's run Solid Verify and run the simulation. You can see that most of the machining or the volume removed was removed using 2D iMachining. So bulk of that has been already been done by iMachining 2D, and the internal small areas are now being handled by iMachining 3D. Now this is like 34 minutes for the entire part. Okay, Right. We can then apply our HSR strategies. For example, we are going to cut the part from another side because I'm using a 5-axis machine. So I'm going to cut the part from the second side to machine the remaining material. So I use HSR. The best part about SolidCAM is that the stock is being constantly updated and it gets passed on from process to process. I don't have to save or do anything. For example, you can see this, run the simulation, solid verify. Okay. Let's remove the single color and start. You can see that from this side, I'm cutting it. And the same methods can then be extended over from all the other sides, wherever it's possible, and then apply our finishing strategy. So what is more important here, the takeaway from this entire process is that, first of all, iMachining, when you're cutting such tough materials, it helps you to bring the best out of your cutting tool. It helps you to bring the best out of your machines. What you are probably using in a conservative way, iMachining opens that up completely. Let me show you another part. Okay, this was a classic part. Now this was for one of my customers because they wanted to buy a machine and they wanted to check the kind of MRR the machine generates. So they evaluated several machine tool vendors, and if I measure this part, this is about 250 by 64, and the height is about 39 millimeters, and the cutting depth is about 31 millimeters. Okay. So they asked several machine tool people to come up with estimated time to rough this part. Several people started at 40 minutes, went up to 1 hour because it's a pretty big part, and the material was stainless steel, PH17-4. That's like 50 HRC, 52 HRC. It's really tough cut this material. So based on the material and the machine conditions, the estimates were given up. What did iMachining come up with? And this part was done in front of the machine tool people itself to show how best their machines could handle. For example, to rough out this was done at level 6 turbo because the machine had got pretty good spindle power. So at level 6 turbo, this machine, iMachining generated parameters of an RPM of 6,000 and a feed rate of 11 meters at a depth of cut of 31 millimeter. It really sounds impossible. People might think that I'm joking that we are come up with these values, but this part was actually cut at these values. Now, if I run the simulation, okay, first we did the upper slopes because we did not want to cut the slopes later on. Okay, and we ran the machining. It just took, it's 45 here, but it took about 1 minute 6 seconds on the machine to open up this pocket on SS PH17-4, 50 HRC. Okay. Similarly, we have got the other areas, 1, 2, 3, 4, and 5. All these areas were cut. So if I run the entire simulation for you, we had estimates of about 2.5 hours, 3 hours, and so on from various cutting tool manufacturers and machine tool manufacturers for this particular part, because trust me, this material is very difficult to cut. And the estimates that the customer was looking was under an hour to cut this part, because that's where he makes money. Because if he exceeds these values or this time, he starts losing money. It appears that the tool is stationary, but it is not. It's actually moving. So time generated was about 58 minutes. This part was done much earlier than that, because the first tool part that took about 20 minutes was regenerated using a much more aggressive pattern, and we generated this part under 45 minutes of cutting. So what is important here is that iMachining, in conjunction with the things that I told you of tool holding, the tool geometry, the fluid coolant, kind of percentage mixing that we need to do, work holding, together with all this, with iMachining, like an icing on the cake, you can actually machine any tough to cut material like Inconel, stainless steel, titanium, effectively, not compromising on your tool life, not compromising on your spindle load, and end of the day, you make money. All right, I conclude my webinar. It was a slightly lengthier one. If there are questions, I would be more than glad to take questions from all of you. Eddie, if there are questions, please let me know, and I'll answer them, or I'll rather try to answer them.
Thank you very much, Amod. It was a great webinar. Thank you, and we'll see all our attendees, I hope, next week also. Thanks to all,
Thank you,
and goodbye.
Thank you.